We are designing the connections between flange and web, and we are designing the connections between flange and web, and we have calculated the shear force, the maximum shear force at the junction of the web and flange is given by T or tau is equal to VA y bar divided by I, and we have calculated it to be equal to 557.86 Newton per mm square. All right, we have calculated it. Now we have to design the connection between flange and web using a continuous weld. And how do we do this? We make use of this table. You can see here in this table, this is the table, design capacity of fillet welds. We'll be using fillet welds to design the connection between the flange and the web. All right, and the design capacity of fillet welds is shown in this table. Here from this side you can see there is leg length in mm, and there is design capacity per unit length. Shop welded, site welded, this is with Fe 410 and with these electrodes, and this is Fe 540 and shop welded. Now we will be using site welded, these fillet welds, and we have to see what size of weld will be requiring, which will be having strength enough to resist this thing. This is the maximum shear force at the junction of flange and the web. All right, this is the maximum shear force at the junction of the flange and web, and this is given by this. We have to design connection between flange and web using a continuous fillet weld, which will be having strength enough to bear this shear force. All right, so here in the table you can see this is the design capacity per unit length of the fillet weld, and if I'll be using a leg length of 4, I'll be having design capacity of 0.529 kilonewton per mm for shop welded and 0.442 kilonewton per mm for site welded. If I'll be using a leg length of 5 mm, I'll be having a design capacity of 0.661 kilonewton per mm for shop welded and 0.553 kilonewton per mm for site welded. What is my shear force? It is 557.86 Newton per mm square. All right, this is my shear force, and I should be having strength enough to bear this shear force. That means I have to provide leg length of the continuous fillet weld in such a way that will be able to bear the shear force. So for example, in the table you can see if I'll be providing a leg length of 4 mm, that will be inadequate because my shear force is more than the design capacity of the fillet weld shown here. If I'll be rather instead of 4, if I'll be using a leg length of 5 mm for my continuous fillet weld to be provided for the connection between flange and the web, I'll be having a design capacity of, if I'll be going for shop welded, it will be having a design capacity of 0.661 kilonewton per mm, and it will be having a design capacity of 0.553 kilonewton per mm for site welded. All right, but we are going for shop welded, and that means we'll provide a leg length of 5 mm, which is having a strength of, with a strength of how much in the table? If I'll be providing leg length of 5 mm, my design capacity of fillet weld for shop welded weld is 0.661 kilonewton per mm, that is 661 Newton per mm. All right. So I'll be use 5 mm fillet weld on either side. All right. So that's how we designed the connection between the flange and the web. We designed it by using a fillet weld of 5 mm leg length, and which will be having a strength of 661 Newton per mm. All right. And this fillet weld of 5 mm leg length is good enough to resist the shear force that is coming on the junction of the flange and web in this girder. All right, moving on, we have to now design the intermediate stiffeners. We designed the connection between flange and web. We used 5 mm continuous fillet weld having a leg length of 5 mm, of course, and the strength of 661 Newton per mm, and that is good enough to resist the shear force that is coming, and that is generated between the junction of flange and web. After that, the next step in this question is to design the intermediate stiffeners. Intermediate stiffeners, all right? Step by step, we are designing this steel trussed bridge, all right? Now we have to design these intermediate stiffeners, all right? And what is the role of these stiffeners? Vertical stiffeners in a steel truss bridge are required to prevent web buckling. All right, vertical stiffeners in steel truss bridges are required to prevent web buckling under shear stress. This must be noted by the students, that we do provide vertical stiffeners in a steel truss bridge to prevent the web buckling under shear stress, especially in areas with high shear forces or concentrated loads, and to improve overall shear capacity of the structure. All right. So these intermediate stiffeners, which will be vertical stiffeners, these are provided in a steel truss bridge, and these are required rather so that they will prevent the web buckling under shear stresses, and they are especially used in areas with high shear forces or concentrated loads, and their role is also to improve the overall shear capacity of the structures. Now we'll see in what situation we need which type of a stiffener. If D by T ratio, please note this carefully, is greater than 90, vertical stiffeners are provided. All right. If D by T ratio is greater than 90, vertical stiffeners are provided. If the same D by T ratio is greater than 200, horizontal stiffeners are provided. We have to see what type of intermediate stiffener we have to provide in our steel truss bridge, and that will be dependent on our ratio of D by T. If it's greater than 90, vertical stiffeners are provided. If it's greater than 200, horizontal stiffeners are to be provided. If it's greater than 250, additional horizontal stiffeners are provided. If it's greater than 250, additional horizontal stiffeners are provided. And if it's greater than 400, section has to be redesigned. All right. If D by T ratio is greater than 400, section has to be, if it's greater than 400, section has to be redesigned. So please note that intermediate stiffeners that we have to provide in our steel truss bridge is dependent on the ratio d by t. If it's greater than 90, we have to provide the vertical stiffness. If it's greater than 200, we have to provide the horizontal stiffness. If it's greater than 250, we have to provide the additional horizontal stiffness. And if it's greater than 400, then section has to be redesigned. And if it's greater than 90, we'll be providing the vertical stiffness, and the vertical stiffness in steel truss bridges are required to prevent the buckling under shear stress, and they also improve the shear capacity, overall shear capacity of the structure, and they are especially provided under the areas which are having high shear forces or concentrated loads. Now in this question, the first thing that we have to check for designing or using, or for checking rather, what type of stiffener we have to use, we have that is wholly and solely dependent on the ratio d by t. Now let's check our d by t ratio. What is our d? The depth of the web, 1000. Thickness is 10. So our d by t ratio is 100. So it falls under the category number 1, that our d by t ratio is greater than 90. It is not greater than 200, so we are not providing horizontal stiffness since it's greater than 90. So vertical stiffness are to be provided. Vertical stiffness, since our d by t ratio in our bridge is greater than 90, so vertical stiffness are required. And spacing between the stiffness, our intermediate stiffness in this type of bridge is now a vertical stiffness, and the spacing between them is given by spacing between the stiffness is given by 0.33d to 1.5d. All right, so let's check if it goes in the what is d? 1000. And what is the range? It goes in the range of 330 mm to 1500 mm. That is the vertical stiffness that we are going to provide. Since our d by t ratio is greater than 90, so we have to provide the vertical stiffness, which will be having a role to prevent the web buckling under shear stresses, and they will also improve the overall shear capacity of the structures, and the spacing between them should lie in the range between 330 mm to 1500 mm. Let us adopt a spacing of, say 1000 mm. Hence our C, that is spacing between the vertical stiffness, is 1000 mm. All right. Let me rub it first. After that, we have to check some more things in case of these stiffeners. In case of these stiffeners, lesser clear panel dimension should be less than, or is less than, 180 times thickness of the web, and the greater clear panel dimension is less than 270 thickness of the web. And as already discussed, minimum spacing of vertical stiffeners is how much? 0.33 times depth of the web. Minimum spacing of vertical stiffener 0.33d, and maximum spacing of vertical stiffener, how much? 1.5d. That's why we just wrote that spacing is in between the range this much. All right. After that, we'll be checking, since we adopted a spacing of 1000 mm, so our C is 1000 mm, greater unsupported panel dimension of the web. Greater unsupported panel dimension of web. Greater unsupported panel dimension of the web should be less than 270 times thickness of the web. That means 1000 mm. It should be less than 270 multiplied by thickness of the web. How much? 10. That is 1000 mm is of course less than 2700 mm. Hence, it's correct and safe. So the greater unsupported panel dimension of the web, which is 1000 mm, it is less than 2700 mm, which is as per the design specifications for the vertical stiffeners. All right. Now these intermediate stiffeners, which is a vertical stiffener in our case because it is as per the d/t ratio, which came equivalent to how much? 100. So it was just greater than 90. It fell in the category number 1. So our intermediate stiffener in this case of a steel truss bridge is vertical stiffeners. Now these intermediate stiffeners, which can be vertical stiffeners, horizontal stiffeners, but in our case it's a vertical stiffeners. These intermediate stiffeners are designed to have a minimum moment of inertia, which is specified as, I'll write it down for you. The intermediate stiffeners are designed to have a minimum moment of inertia, which is given by you can write it, which is given by a formula, that is 1.5 d cube divided by c cube, where d is the depth of web. You must note it. D, the thickness of web. And what is C? Spacing between the stiffeners. Or I may write it down as spacing of stiffeners. All right. So these intermediate stiffeners are designed to have a minimum moment of inertia, which is given by this formula, and these are the things what we have represented in the formula. So we'll substitute the values and we'll see what is the minimum moment of inertia which is resisted by our intermediate stiffeners. So our intermediate stiffeners are designed to have a minimum moment of inertia, which is given by this formula. Let me substitute the values. 1.5, depth of web 1000, thickness of web 10, spacing between the stiffeners we just adopted 1000. So by calculations, this is equal to 150 into 10 raised power 4. Unit will be mm raised power 4 because this is moment of inertia. All right. So the intermediate stiffeners are designed to have a minimum moment of inertia, and which is given by this 150 into 10 raised power 4 mm raised power 4, or I may write it down as 15 into 10 raised power 5 mm raised power 4. Note this moment of inertia. So our intermediate stiffeners are designed to have a minimum moment of inertia, which is given by this formula, and we calculated this to be equivalent to 15 into 10 raised power 5. Unit is mm raised power 4. All right. After that, the outstand of this stiffener, shall not be greater than 16T. These are some of the design specifications for the stiffeners, and the outstand of stiffener shall not be greater than 16t for roll sections and 12t shall not be greater than 12t for flats. Alright, where t is the thickness of the section. Alright, so outstand of the stiffener shall not be greater than 16t for rolled sections and shall not be greater than 12t for flats, where t is the thickness of section or flat. Let us assume that we are using a 10 mm thick flat plate. All right, so outstand of stiffener should not be greater than how much? 16t. Please do not confuse yourself with the flat that I wrote down here. If we are using a 10 mm thick plate, the outstand of the stiffener shall not be greater than 16t for roll sections and shall not be greater than 12t for flats. Since we have roll sections, all right, in the very beginning of the question, we are using rolled steel sections. So if we are using a 10 mm thick plate, our outstand of the stiffener shall not be greater than 16t. 16, and how much is the t? We are using a 10 mm thick plate. So maximum width of plate should not be greater than 16t, which is 160 mm. Now we have to adopt a plate thickness we have already chosen, 10 mm, and the maximum width of the plate should not be greater than 160 mm. Let's adopt a plate of 10 mm cross 80 mm. Having moment of inertia as, now we have to calculate the moment of inertia of this plate. This is a rectangular plate. All right, we have adopted a plate having 10 mm thickness and width as 80 mm. All right, now listen carefully. Before proceeding any further, let me tell you about the moment of inertia of the rectangle. This is to be noted here to avoid any confusions whatsoever. Moment of inertia of a rectangle about the axis passing through the centroid is given by bh cubed by 12, where b is the width and h is the height. This is the moment of inertia of the rectangle about the axis passing through its centroid. What is the moment of inertia of a rectangle about centroid axis but perpendicular to its base? We'll be reversing hb cubed by 12. This is the moment of inertia of the rectangle about the centroidal axis but perpendicular to the base. This was about the centroidal axis. This is perpendicular to the centroid, about the centroidal axis but perpendicular to the base. Now the moment of inertia of the same rectangle about an axis passing through its base is how much? Axis passing through base. Moment of inertia, I'm repeating once again, moment of inertia of a rectangle about the centroidal axis is given by bh cubed by 12, where b is the width, h is the height. Moment of inertia of the same rectangle about the centroidal axis but perpendicular to the base is given by hb cubed by 12. now we have to see what is the moment of inertia of the rectangle about an axis passing through its base. Because we are designing the intermediate stiffness and we have adopted a plate, we are not using the moment of inertia about centroids. Rather, we are using the moment of inertia of the same rectangular plate about an axis passing through its base. And that is given by PHQ by 3. Please note this. Moment of inertia of a rectangle about an axis passing through its base is given by BH by 3. Alright. And perpendicular to its base, it's given by, if I'll be using this formula, this is TH by 3, where T is the thickness of the plate and H in this case is the outstand of the stiffness. Please note this. T is the thickness of plate and H in this case is not the height and B is not the width. T is thickness and H is what? Outstand of stiffness. How much is our thickness of plate? 10 mm. We have adopted a plate having the dimensions of 10 mm cross 80 mm, and 80 mm is the outstand or the maximum width of our plate, which is how much? 80 mm. Now, moment of inertia is given by THQ by 3. It is about an axis perpendicular through its base, and this will be given by 10 multiplied by 80 cube of it divided by 3. By calculations, it is 17 into 10 raised power 5 mm4. So this is the moment of inertia of the plate that we adopted to be used for our stiffener, a vertical stiffener, and it came equivalent to 17 into 10 raised power 5 mm4. But what was our design moment of inertia? It was how much? We just discussed that these intermediate stiffeners, which is a vertical stiffener in our case, these are designed to have a minimum moment of inertia, which was given by 1.5 t cube by c cube, and by calculations it was 15 into 10 raised power 5 mm raised power 4. And the plate that we adopted to be chosen for our stiffener, we adopted it of the dimensions 10 mm cross 80 mm. T is the thickness of plate, and this H, this is the outstand of the stiffener, which is 80 mm. It should not be greater than 16 times T, that is for the roll sections that we have, and it is definitely not greater than 16 times thickness, that is 160 mm. We just chose 80 mm. All right. And if we'll be adopting this plate 10 mm by 80 mm, this is having a moment of inertia of 17 into 10 raised power 5 mm raised power 4, which is definitely greater than 15 into 10 raised power 5. Hence, our section is absolutely safe. All right. And once again, repeating it to you that we have to design the intermediate stiffeners in a steel truss bridges for various purposes, and this is absolutely dependent on the ratio d by t. If d by t is greater than 90, we have to provide vertical stiffeners. If it's greater than 200, then horizontal stiffeners. If it's greater than 250, then additional horizontal stiffeners are provided. And if our d by t ratio is greater than 400, then our section has to be redesigned completely ab initio. All right. Since our d by t ratio was greater than 90, that means we have to provide the vertical stiffeners, and the vertical stiffeners have a role that they prevent the web buckling under shear stress, especially in areas with high shear forces or concentrated loads. And in addition to prevent the web buckling, they also improve the overall shear capacity of the structure. Our d by t ratio was greater than 90. We chose the spacing, and we also checked for the greater unsupported panel dimension of the web. And these intermediate stiffeners, which is the vertical stiffener in our case, these are designed to have a minimum moment of inertia. This was the design moment of inertia, and we adopted a plate as per the design specifications, 10 mm cross 80 mm. We checked its moment of inertia about an axis, so this is a rectangular plate, and we checked the moment of inertia of the same thing about an axis passing through its base but perpendicular to it, so which was given by the formula th cubed by 3. This is the moment of inertia of a rectangle about an axis perpendicular to its base, passing through its base but perpendicular to it. All right, so this came equivalent to how much? 17 into 10 raised power 5 mm raised power 4. So that is definitely greater than the design moment of inertia, hence our section is safe. Now the last thing that we are doing in case of designing of connections, this is the connection of vertical stiffener to web. All right, you designed a vertical stiffener for the steel truss bridge by adopting a plate 10 mm cross 80 mm. Now we have to design the connection of this vertical stiffener to web. All right, connections of vertical stiffener to web. All right, now we have to design the connection of the vertical stiffener to web, what type of a fillet weld we are using to provide the connection of this vertical stiffener to web. Please note down that the connection of the vertical stiffener to web is designed to resist a horizontal shear force of not less than 125 T square by H kilonewton per meter, where T is the thickness of the web and in mm, and H is the outstand of the stiffener. Outstand of stiffener. The connection of vertical stiffener to web is designed to resist a horizontal shear force of not less than this thing. So this is horizontal shear force. All right. So let's design the connection. So shear on welds connecting vertical stiffener to the web is given by connecting vertical stiffener to web. Vertical stiffener to web is given by 125 T square. How much is the thickness of web? 10. H is the outstand of the stiffener. How much is the outstand of stiffener? 80 mm. All right. So by calculations, this is 156.25 kilonewton per meter. Or I may write it, it's 156.25 Newton per mm. All right. So the connection of the vertical stiffener to web is designed to resist a horizontal shear force of not less than this thing. And by calculation, that means our shear on the welds connecting our vertical stiffener to web is how much? 156.25 Newton per mm. Since we are designing the connection of our vertical stiffener to web, and the shear on the welds connecting this stiffener to the web is given by 156.25 Newton per mm. So accordingly, we have to see what size of weld we are or we have to provide. Size of weld. Alternatively, this is another way of choosing the size of the fillet weld. S, it is given by F divided by 0.707 into tau, where F is the shear on weld or shear force on welds, and tau is the shear stress on the welds, and 0.707 is there in the formula. Now I have this thing, this is a constant. I have to see what is this thing. Shear stress on welds. We'll again go to the same table we used earlier. I'll be using a side welded fillet weld, all right, and which is having shear stress of how much? 158 MPa, Newton per mm square. All right, the shear stress on the welds in case of the side welded fillet weld is how much? 158 Newton per mm square. And we'll be using the same thing to calculate the size of our weld. All right. How much is the shear force? It is 156.25 Newton per mm. 0.707. Shear stress 158 Newton per mm square. By calculations, this is equal to 1.39 mm. All right. Also, effective length of the weld should not be less than 10 T. Effective length of weld, we are designing both size as well as the length of the weld. Effective length of the fillet weld should not be less than 10 T. How much is T? 10. So it's 100. Effective length of the weld should not be less than 10 T. Now let us design the weld. So we'll be providing 100 mm long and 5 mm leg length fillet weld, or this is the size, alternately on both the sides. All right. So our connection of vertical stiffener to web has been designed, and we have provided 100 mm long, 5 mm size fillet weld alternately on both these sides. All right. So this was about designing the connection of the vertical stiffener to web, and we designed it as per this formula, where F is the shear force on the weld, which we calculated by the formula 125 T square by H, right? And this tau, this is the shear stress on the welds, all right? And we have different categories over here in this table, which gives us the design capacity of fillet welds, and we use the side welded one having the shear stress of 158 MPa. We use the same thing, and we designed our connection between vertical stiffener to web, and we used a 100 mm long fillet weld having a size of 5 mm alternately on both the sides. That is how we design the connection of vertical stiffener to web. Now the last portion of the steel truss bridge is to design the steel truss itself. Alright. So we completed first deck slab, then we completed stringer, then we completed cross girder, then we completed all the connections whatsoever. Now the last part in this steel truss bridge is the truss itself. We have to design the truss, the Warren truss that we have used. All right. So this is the remaining part. We have done every other thing. Let me show you in the figure. This is the Warren truss, wherein we have used 6 panels of 5 meter each. Total span is 30 meters. Now we have to design this Warren truss, and this is the last part of this design process of a steel truss bridge. All right, but before that, we'll take this in the next video lecture. Before that, I'll show you the reinforcement details of the slab. In the very beginning, we designed our deck slab, and we designed it for various reinforcements. In the shorter span and the longer span, we use distribution steel as well, but I didn't show you the diagram showing the reinforcement details. So this is the diagram showing the reinforcement details of our deck slab. This is the cross section of deck slab. These diagrams are not drawn to scale, please mind that. This is the depth of this slab, 200 mm. This is the wearing coat, its thickness is 100 mm. This is the cross section of the deck slab. We have used 12 mm dia bars at the rate of 100 mm center to center along the shorter span. So this, and we have used 12 mm dia bars at the rate of 300 mm center to center along length. So these will be shown like this in the cross section, and this is along the shorter span. This is along length. Moreover, we have also used distribution steel of 8 mm at the rate of 200 mm center to center spacing, which is shown like this or here. And here you can also see these are the 12 mm dia bars at the rate of 300 mm center to center spacing. And these are the 8 mm distribution steel, because distribution steel is everywhere, all right? It's distributed everywhere. 8 mm dia at the rate of 200 mm center to center spacing. This was our curb stone having a width of 600 mm, and the effective width of the carriageway, it was 7.5 meters. So these are the reinforcement details of the deck slab, and I have shown the cross section here. No, it's just not the longitudinal section. This is the cross section, and these are the reinforcement details, and the diagrams have not been drawn to scale. Please mind that. So that is how we draw the reinforcement details of a deck slab, which was the first step that we designed in this case of a steel truss bridge. All right, you can once again say it clearly. I hope it's clear to you. The diagram is clear to you. That's how I have designed reinforcement details. So our designing of a steel truss bridge, we have completed the 4 parts. The last part that is remaining is that we have to design the Warren truss itself. That will be taking in the next video lectures, God willing. So we have completed deck slab, the stringers, the cross girders. We have checked for various stresses, bending stresses, shear stresses. We have designed the connections as well. Now the last thing that remains is that we have to design Warren truss, which we'll be taking in the next video lecture, God willing.